Hi, welcome to another episode of this Gravity series. I'm sure you've all heard about Isaac Newton and that apple that fell on his head, and how that was a huge deal for our understanding of gravity. Well, let's talk about it. Isaac Newton is one of the most important scientists in human history. One of his main contributions was to describe how the world works with formulas. Newton unified Johann Kepler's theory of planetary motion with Galileo's theory of falling bodies. Newton published his laws of motion and universal gravitation in the Mathematical Principles of Natural Philosophy, commonly known as Principia, in 1687. Newton's first law of motion states that objects continue to move in a state of constant velocity, which can be zero unless acted by an external force. The tendency of an object to resist a change in motion is known as the inertia, and objects that are moving at a constant velocity are said to be in an inertial reference frame. Galileo had first suggested this law, but it had not been universally accepted because it contradicted Aristotle's laws of physics. Newton's second law shows how an object will be affected if an external force does act upon it. This law states that the rate of change of momentum of a body is proportional to the result force acting on it and will be in the same direction. Newton's third law states that the force of an object is always due to another object. All forces act in pairs that are equal in magnitude and opposite in direction. This is why you feel recoil when you strike an object and why you do not fall through the earth due to the pull of gravity. Newton's law of universal gravitation states that every mass attracts every other mass in the universe, and the gravitational force between two bodies is proportional to product of their masses and inversely proportional to the square of the distance between them. Here, for the two objects that are orbiting a common center of mass, like the Earth and the Moon, M1 is the mass of the less massive object, like the Moon, and M2 is the mass of the more massive object, like the Earth. F1 is the gravitational force produced by M1, the Moon, and F2 is the gravitational force produced by M2, the Earth. R is the distance between the two masses. Finally, G is a constant that is the same for everything in the universe. Newton stated that the force of gravity is always attractive, works instantaneously at a distance, and has an infinite range. Most importantly, it affects everything with mass and has nothing to do with an object's change or chemical composition. Newton's Cannonball thought experiment. In 1728, Newton demonstrated the universality of the force of gravity with his Cannonball thought experiment. Here, Newton imagined a cannon on top of a mountain, as you see here in this image, and without gravity, the cannonball should move in a straight line according to the first law of inertia, as we saw. If gravity is present, then its path will depend on the velocity. If it's slow, then it will fall straight down. If it reaches the orbital velocity, where the gravitational force equals the centripetal force, then it will orbit the Earth in a circle of ellipse. If it's faster than the escape velocity, when the kinetic energy is equal to the gravitational potential energy, then it will leave the Earth's orbit. Nowadays, we use the third law of motion to find out how much force we must put on a rocket to launch a satellite in orbit or to travel to the moon. And we know this as the escape velocity, as we can see in this next video.
Start. 2, 1, boost ignition, and liftoff of the Space Shuttle Discovery, returning to the space station, paving the way for future missions beyond. Discovery's 23 engines now about 1.5 miles downrange, tracking over 740 miles an hour. Everything working in flight. Engines beginning to rev up. Speed approach.
Everything can go at throttle up.
Then why Earth orbits the Sun? Well, the Earth has a velocity in the direction perpendicular to the force of the Sun pull. If the Sun wasn't Earth, the Earth would travel in a straight line. But the gravity of the Sun alters its course, causing it to travel around the Sun in a shape that's very near to a circle. This is a little hard to visualize, so let me give you an example of how to visualize an object in orbit around the Earth. The basic reason why the planets revolve around or orbit the Sun is that the gravity of the Sun keeps them in their orbits. Just as the Moon orbits the Earth because of the pull of Earth's gravity, the Earth orbits the Sun because of the pull of the Sun's gravity. Why then does it travel in an elliptical orbit around the Sun rather than just getting pulled in all the way? Well, as in the Newton Cannonball experiment explained before, the Earth is traveling fast enough to continually miss the Sun and keep always falling towards the Sun as the centrifugal force and the centrifugal force compensate mutually according to third Newton law, and the resulting path is the orbit. There are two opposing forces acting on the planets: gravity pulling them inward and the inertia of their orbit driving them outwards. The planets are trying to fly out in deep space, but the gravity of the Sun is pulling them into a curved orbit. Curiously, Newton was not able to measure and calculate the value of G with capital letter, the gravitational constant. It was a very intelligent guy, 100 years later, the person, who was able to design a brilliant experiment to find this. Don't miss the next video because I'm going to explain more about this brilliant guy and how he found the value of the gravitational constant. Bye!